An apple fell on Isaac Newton's head, and then there was. Gravity was the first parameter that split from the grand unified theory. Gravitational force is the most influential force in a universal scale. After the Big Bang, there were the emergence of four universal parameters. That's the strong nuclear force, the weak nuclear force, the electromagnetic force, and then gravity. I keep saying gravity because it isn't a force, and I will explain. Isaac Newton was a British scientist that proposed that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Therefore, he explained gravity as the effect masses exert on each other, and that is why bigger objects in space exert a greater gravitational force. For example, the gravitational force of the Sun is much greater than that of the Earth, analogous to their size comparisons. So Newton's shell theorem tells us how different parts of the mass distribution affect the gravitational force measured at a point located a distance from the center of mass of the distribution. Newton's take, however, failed to account for the precession of the perihelion of Mercury's orbit around the Sun. Every century, Mercury's perihelion of orbit drifts 0.001 degrees. Then Albert Einstein came into the picture. Einstein said, "The happiest thought of his life is a man falling from a roof." As funny as that sounds, he explained gravity as the bending of space-time. According to the general theory of relativity, gravity is not a force. Weightlessness is what you feel when you are in space. A man free falling is an example of an inertial observer. Just like a person in space. So Einstein's theory of equivalence tells us that you experience the same thing being still on the surface of the earth as a person in a rocket accelerating. An accelerometer that is used in measuring acceleration would read that you are standing still on the surface of the earth. You are actually accelerating upwards. So then the question appears, if someone is approaching Earth in a rocket, what pulls the person towards the face of the Earth if you are not talking about gravity? This is where the explanation of a straight line comes in space. So we were made to understand that a straight line is the shortest route between 2 points. That is true on a small scale. But when we are talking about a large scale, like the fabric of space-time, a curve is the shortest route. Geodesics is a study of the path in space-time where space is made flat. As in when we make the surface of the earth flat, the route airplanes take from one destination to another looks curved. This is what an inertial observer would observe in space. Since the earth curves space-time around it, an inertial observer will see a rocket moving around the earth in a helical pattern. Acceleration is not relative, it is absolute. If a person is in free fall, he is in an inertial frame of reference and could tell you are accelerating upwards. Therefore, if you jump up, the earth accelerates upwards and catches up to you. This upward movement of the earth is as a result of the helical accelerating movement of the earth moving through space-time. An inertial frame of reference is one which the motion of a particle is not subject to forces in a straight line at constant speed. An inertial frame moves with constant speed with respect to other inertial frames. The thing is, as we are standing on the surface of the earth, we might think we are at rest, but so far as we are not feeling weightless, we aren't. We are not inertial observers. We are accelerating upward in space-time. Someone falling from a roof who is in an inertial frame of reference will see you standing on the ground at rest to be moving upward at 9.8 meters per second. If you were in flat space-time, then the second derivative of your position is equal to your acceleration. But since we are not in flat space-time, we account for curvature of space-time multiplying velocity squared. Therefore, in curved space-time, we need to accelerate in order to stand still. Rockets in space accelerating aren't really accelerating, but it is the space-time accelerating into them. Then another question pops up. If it isn't gravity that is holding the planet in position from the sun, and it is because they are moving through space-time, then why do they move in the same circular path all the time? The answer is they don't. Don't forget, space-time is four-dimensional, and so the movements of the planet are helical, not circular. Matter tells space how to curve. Space-time tells objects how to move. Gravity bends light only in an accelerating frame of reference. This is how Einstein was able to predict that gravity bends light, where an experiment was conducted during a total eclipse. And during that eclipse, light was seen around the sun, showing the bending. So, if gravity isn't a force, then what is a force? A force is an influence that causes an object to change its velocity. And clearly, nothing is bothering these planets or us, for that matter, to cause us to change in direction other than external forces, gravity excluded. So, with this, I hope we've all been enlightened on what actually gravity is. Thank you very much for listening and watching. Until next time, this is Einstein in a Flash. Please like and subscribe.